Alright, this is a fluid mechanics group project, or group number 20. Our topic is hydrofoils. It's a very simple concept, really. So these are a few questions we will be answering throughout the entire presentation. A hydrofoil is essentially a wing-like structure that lies underneath the surface of water and is attached to a boat or board-like structure that lies above the water that causes lift of the structure to increase the speed of the vessel.
As a marine vessel moves through water, it is constantly being slowed down by the drag force from the friction due to water. A hydrofoil reduces the amount of area water can come in contact with the boat, thus reducing drag. As a marine vessel increases its velocity, lift is created from the hydrofoil and sends the vessel above the surface of the water. Taking a closer look at how this works, based on the diagrams below, the two water molecules strike the front of the hydrofoil at the same velocity. The path traveled by the top water molecule is longer than the path traveled by the bottom molecule. However, both molecules do not reach the endpoint at the same time, as seen in the diagrams. The top molecule travels over a longer streamline but has a higher velocity. The bottom molecule travels over a relatively shorter streamline with a slower velocity. Taking a look at the bottom right diagram, we can conclude that the molecules on the upper surface travel faster than the water molecules on the lower surface, thus creating a pressure difference on both sides of the hydrofoil. A higher velocity results in a lower pressure, and a relatively lower velocity results in a relatively higher pressure. As an end result, this creates a lift force from the pressure difference. We can explain this phenomena from Bernoulli's equation. When we do this, we must take into consideration that Bernoulli's equation can only be used when a molecule flows along the same streamline and not across streamlines. In this equation, we are working in units of pressure and comparing the pressure at the front of the hydrofoil to the back along the same streamline, as well as the kinetic energy associated from the velocity. We can neglect any height because delta z, or the change in height, is minimal or close to zero.
Bernoulli's principle or equation is of vital importance in regards to how a hydrofoil works. The general summation would be that it evaluates the conservation of energy from one instance to another for a fluid. The equation reads P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. In this equation, P is the pressure in pascals or pound force per feet squared, rho is the density in kilogram per meter cubed or pound force per foot cubed, V is the velocity in meters per second or feet per second, and H is the height in meters or feet. More specifically, 1/2 rho V squared is the kinetic energy per unit volume, and rho GH is the potential energy per unit volume. The subscripts refer to which scenario the variable is referring to. The hydrofoil causes the fluid above it to move at a higher velocity, and using Bernoulli's, something must decrease on that side of the equation to maintain the conservation of energy, and in this case it is the pressure. The fluid below the foil has only a slight velocity change, if any change at all, and this provides a steady pressure force beneath the foil. The decreased pressure above the hydrofoil and steady pressure below creates a lift force directed upward, lifting it out of the fluid against gravity.
The magnitude of the lift generated by an object depends on the shape of the object and how it moves through the air. For thin airfoils, the lift is directly proportional to the angle of attack for small angles, within plus or minus 10 degrees. For higher angles, however, the dependence is quite complex. As an object moves through the air molecules stick to the surface. This creates a layer of air near the surface called a boundary layer that in effect changes the shape of the object. The flow turning reacts to the edge of the boundary layer just as it would to the physical surface of the object. To make things more confusing, the boundary layer may lift off or separate from the body and create an effective shape much different than the physical shape. The separation of the boundary layer explains why aircraft wings will abruptly lose lift at high angles to the flow. This condition is called a wing stall. The angle of attack is defined as the angle between the free stream air and the chord line connecting the leading edge and the trailing edge. For most cases, increasing the angle of attack increases the coefficient of lift. There is, however, a critical angle where the coefficient of lift becomes a maximum and an increase in lift is no longer possible. This creates separation of the airflow between the airfoil and can be thought of as an aerodynamic stall, causing no lift generation and a large drag force on the airfoil. As you can see from the figures on the right, with an angle of attack being 0 degrees, a wing will stay fixed at one elevation. However, if the angle of attack rises to be greater than 0, the wing will rise in elevation, and vice versa for an angle of attack less than 0, where the wing will drop in elevation. The angle of attack has a large effect on the lift generated by the wing.
There are a wide range of real-life applications based off fluid dynamics behind hydrofoils. Just as on the slide, we have listed 8 everyday products, including everything from a spoiler on a car to propellers for an airplane. The top 2 images illustrate how the hydrofoil creates a perpendicular lift force and a parallel drag force on a sailing boat and a wind turbine. Next, the bottom left image demonstrates how the air flows around a bladeless fan. Lastly, the bottom right image is a hydrofoil board being used. You can see how the high versus low pressure creates a lift force, causing the board to be pushed out of the water. The benefits of hydrofoils vary from product to product. The first example is a boat. As a hydrofoil equipped aircraft increases in speed, the hull drag is greatly reduced because it is lifted out of the water. This provides a corresponding increase in speed with fuel efficiency. A wind turbine can capture more energy and operate more efficiently in areas with lower wind speeds because when a flat blade pushes against the wind and the wind pushes back against the blade, resulting in a slower rotation. This is not the cause with a curved blade, since it reduces the drag force, increasing the efficiency. Last, a car spoils unfavored air movement across the body of a car, which in turn increases the downward force on the rear of the vehicle, improving and maintaining traction while increasing fuel efficiency.
Here are the references used to create this video. Thanks for watching.